All right. Yeah, welcome everybody to my talk, which is on innovations in medical technology, specifically addressing the ability of tumor identification in cancer research. And here at the University of Wuppertal, we are looking into sensor technology at terahertz frequencies to identify healthy tissues from cancerous tissue. So we will have first in my presentation an introduction to medical technologies using terahertz radiation, and we are going to look into the differences between far field and near field techniques, which give us some improved resolution. And then we move in the main part into some sensor technology. We are presenting some highly integrated sensor array that allows us to take real-time terahertz imaging data and visualize that for tumor margin identification. And at the end, we are going to look out a bit into the vision of the Terahertz NRE project and what are the next steps that we are working on. All right, so let's look first into the terahertz frequency range and compare it to the typically visual range that we are all able to see, which is shown here in blue. And in this chart here, you see the attenuation of electromagnetic radiation in atmosphere over frequency. So you see the range that we typically refer to when we talk about terahertz is the sub-millimeter wave frequency range, roughly spanning from 100 gigahertz to 10 terahertz. So that's well away and separated from the visual range shown in blue. And what you see here is that in atmosphere, you have a very pronounced strong resonances of various kind of gas molecules. This is water, oxygen, for instance, causes vibrational and rotational resonances, which already show that there's a strong interaction between terahertz radiation and gases, and as well as solids. Although at solids, we don't have that many strong resonances like in gases, and therefore what we are typically trying to do is to measure the permittivity, which is the dielectric constant of a solid. And we use that for identification of different materials and tissue, also in this work that I'm going to present. Now, just keep in mind that most of the inspection techniques are happening in the visual range, and that we are considering this extra terahertz range as an add-on to existing medical diagnostic techniques. All right, so let's look into the context and objective. And what we are primarily interested in here is breast conserving surgeries, where typically the primary tumor is removed from the patient, and then the medical doctor kind of visually inspects the tissue and looks for tumor margin. That means what they really want is a clean margin. That means a cut through the tissue does not show any cancerous tissue reaching up to the edge, which they call a dirty margin. And if that's the case, basically, typically the patient has to undergo a second surgery. And that already happens 15 to 20% of the time. So if it's possible to kind of come up with an inspection technique that does not need a sample to undergo a sectioning process in the lab, that would really speed up the time the patient spends in the hospital and in the emergency room. And therefore, that is really something that could revolutionize kind of the procedures that we are currently applying to as many as maybe 2 million new cases per year worldwide. So that's a histological check and something that we are investigating currently as part of the Terahertz NRE project. Now let's see first how these samples typically look like. And here you see one of these typical cases where a primary tumor has been extracted from a patient, and you see different kind of regions. Here, for instance, cancerous region, it's a little bit more white, whereas the adipose fat part here is a bit more in yellow. And of course, you want to make sure that none of that tissue kind of reaches up to the edge of the primary tumor. Now, the question is, would we be able to kind of detect that with terahertz radiation, as I just pointed out, by using the permittivity and the material characteristics? And that is shown here in this measurement that we've done in the far field. So we were looking from distance at the tissue and looked into the reflected waves by extracting the refractive index, basically. And here you see different kind of benign, malignant, or adipose tissue. And you clearly can see that over frequency here from 200 gigahertz to 800 gigahertz, we can still separate these different tissues in this graph. Although we have to say that the difference is diminishing a bit when we go to higher frequencies, as these curves are kind of moving closer to each other. But on the other hand, you see that the increased frequency has a higher resolution because the wavelength is getting shorter. So that's kind of a trade-off right now to optimize kind of the separation of these curves, as well as increase in resolution by moving to higher frequencies. So that's why we picked here a sensor that operates at 500 gigahertz as kind of an optimum for resolution and detectability. Now, but if you're still in the far field, you see, and these are some example tissues that we have taken, that far field imaging for sure is not good enough when it comes to resolution. You see here 3 images, one taken at 310 gigahertz, one at 400, and one at 490 gigahertz. And you can clearly see that although you can maybe see some shadows, you really are not well defined laterally to identify even cells or cancer cells on the level of a couple of micrometers. And that really is the reason, because we are really limited to lambda over 2 at the far field, and in the sub-millimeter wave frequency range, the resolution is just on the level of millimeters and not micrometers. And that's why we have to really think about other techniques like near-field imaging techniques that can resolve a lot of structural details that are much smaller in size, as you can see here in this overview chart. Here you see basically the free space diffraction limit here as this blue curve kind of divides the left and the right side of this graph into 2 parts. And the right side, this is typically what we can use in the far field for macroscopic objects like knife in security applications or keys here in non-destructive testing. But for anything that's smaller in size, like tissue or cells, chromosomes, DNAs, proteins, or viruses, you have to resolve structures that are much smaller than that. And typically for cancer tissue research, you are looking for something like on a resolution of about 10 micrometers at least. And therefore we really need to rethink the way our Terahertz imagers are built to actually use information that we acquire in the near field. And that is kind of shown here in this figure. You see some of the visions that we kind of have in mind here also in the Terahertz NRV project for a terahertz near field imager that is like something like an endoscope that you can actually bring down to some tissue, and you can create a near field image and you can resolve basically the material properties of those cells at a scale that is about the size of a cell itself. Now, what is the technique that we are using here to do that? This is shown here in this chart where we illustrate the principle of a split ring resonator. A split ring resonator basically is an LC resonant circuit where you have an inductive and a capacitive part. Now, if you bring a material or a tissue close to this gap, which is the capacitive part of this resonator, you're basically changing the capacitive part of the tank, and that detunes the resonance frequency. And that is something you can try to detect in an electronic circuit. Now, this is on this chart, you see how this is actually implemented. And as I pointed out at the beginning of the talk, our techniques are something that is building up on standard microelectronics. So we are trying to implement these sensors in a silicon chip, something similar to the chips that you are using in your cell phone, for instance. And here we are trying to attach these resonators shown here on the left side in red, excuse me, to a microstrip line. And then we can send a signal into this resonator and out of the resonator on the other side. Now, this can be used to then figure out the detuning of the resonance frequency. We, of course, model this with an electronic circuit. And here on the right side, you see a cross-section of the process technology that we are using right now. And we then feed the signal into the detector transistor. And that is something then we can read out through typically a USB interface and then show it on a screen. Now here you see the sensing concept. As I said, it's not just sufficient to have just the splittering resonator. We have to generate the terahertz signal with an oscillator, send that in and out of the resonator into a detector transistor, and then the response will be visible as soon as we load the resonator with some capacitive component like the tissue under inspection. Now, when the frequency shift occurs, we don't necessarily have to measure the whole resonance frequency over a large frequency range. It's fully sufficient to just probe the shift at a single frequency here. And that's our oscillator frequency. So we really can simplify this architecture and implement an oscillator basically in every pixel of our imaging system. And this is shown here in this first implementation of this concept, where we have a 128 pixel near field imaging chip. So in one line, basically, we have this 128 sensors with a pitch of 50 micrometers. And then each of these sensors are kind of measured with a signal generated from an oscillator. And on the other side, we have our detector transistors. And then we have all the readout electronics included here. We have ADCs that sample the data, and then this can be brought out to data acquisition system. Now you see the chip is pretty tiny. These are just a few millimeters in size. It's 1.75 times 6 millimeters. And you can attach this chip to a regular FR4 board, and then you can run this chip in first evaluations. Now, the block diagram, of course, shows you the readout architecture, and we don't really have to go into each of these details, but I just wanted to mention that this is a fully integrated sensor technology, what we call a system on a chip, and it's really using standard microelectronics, which I think is a key feature for the technology readiness level to make this really something that could work in a clinical environment. Now, a key parameter to measure would be the lateral resolution that I pointed out needs to be on the level of a couple of microns to resolve chips, resolve cells attached to the chips. And here, to measure this, we have placed a metal needle down to the sensor and moved across it. And then we can kind of capture the step function from 10% to 90%. And the distance between them is kind of giving us the lateral resolution, which for this sensor was in the range of 10 to 12 micrometers. So that is exactly this range where we need to be in order to resolve cancerous cells. Another very important measurement is the sensor response decay. And that means if we are not really in touch with the sensor surface, and we are a little bit away from that, we have, of course, a little bit of different measurement. And that tells us basically how close we need to get with the sensor to the tissue. And according to these measurements, we see that we need to be as close as maybe 15 to 20 micrometers in order to be in a sensitive range for the sensor. So this is really some near field technique, which means you have to be in touch with the tissue. And it's not a far field measurement technique that you have seen as an example at the beginning. And if you want to create an image with that, you have to kind of bring the sensor to the tissue very closely. And that is done here in a measurement stage where we have evaluated the sensor technology. And with that, we can very precisely step the 1D array basically over a 2D surface. And the first object that we looked at is a metallic nickel mesh. You see this mesh here as a terahertz image that we recorded in this setup. And you see that this mesh has a bar width of 50 microns and a pitch of 250 microns. So you clearly can resolve that very nicely. And that really is a very good indication that we have the required resolution to apply that to our specific application. Now, another very nice demonstration is a real-time demo where you can actually take your finger and scan your fingerprint on this sensor. Because we are highly resolved, we can highly resolve the tissue, we should also be able to resolve the fingerprint. And you can move your finger kind of back and forth along the sensor array, and you see on top, you see the real-time response of all these individual sensors. Now, this is uncalibrated data, of course, and you can, through some calibration process, then get the image data that you see here on the right side. And this green picture on the lower right side kind of is the Terahertz fingerprint image, and you can compare that to an ink print on top of it, and you can clearly correlate the characteristic features of the fingerprint also here in the Terahertz image. This scan just took 30 seconds for a 1 kilopixel DPI fingerprint image, and that is for terahertz, of course, a very fast kind of acquisition time. You can also kind of clean the sensor surface. You can also put some isopropanol on it, and you can see the response time of that sensor for that treatment. Now, and of course, the final goal of the project, of course, is to look at cancer tissue. And here you see a breast cancer tissue that was looked at under the microscope. On the left side, you see the typical image that a medical doctor would see when he looks through the microscope without staining. And under the microscope, everything kind of looks the same. It has the same color, the same contrast. But if you try to do this at terahertz frequencies, you can already see some contrast in certain parts of this image. And that is kind of the difference here between terahertz imaging without staining the tissue. And we really can use that data to then measure the permittivity and find contrast between cancerous cells and healthy tissue. And that, of course, is something that we would like to evaluate now in collaboration with the medical partners in our project. And that brings us closer, of course, to this vision that we have to develop basically a more densely array in the future, something like a 2D array, and then you would not even have to scan anymore, and you just press the sensor array onto your surface, and you immediately get a real-time video that can be used during an operation, and that would certainly be something that would improve the quality of life for cancer patients. Now, with this, I would like to close the presentation and thank you for your attention.
Okay, thank you very much, Professor Pfeiffer. And now, before we move on to a Q&A session, we'll continue with Professor Seidel and Svenja Kobel's presentation. Thank you very much.